Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. In this video, we will continue on the chapter 4, Norton Equivalent, or we will also call it as a Norton Theorem. In a linear two-terminal circuit like in this figure, we have terminals A and B. Any complicated circuit or any linear two-terminal circuit can be replaced with a current source in parallel with a resistance. We call it Norton resistance. So for a Norton equivalent theorem, we can replace a two-terminal circuit with a current source in parallel with a resistance. Due to this, we need to find two things. Find the Rn and also to find the In, the Norton current. So to find the Norton resistance, in order for us to find this R Norton, if we have to replace this two-terminal circuit, a complicated circuit here, into this simple form, I Norton in parallel with R Norton, what we need to do is, if we do have something like a load here, R load, we need to remove the load first. So the first step is that you need to remove any load so that you have an open circuit at A and B terminals. And then second, you need to turn off all independent sources. Okay, so let's see if we have on your left side here. So what we have here is basically some current source. How to find this R Norton? What should you do is you need to turn off the independent sources. To turn off a current source, you need to replace this with a open circuit, right? So this is an open circuit. Then whatever equivalent resistance here is actually equal to this Rn, because we basically don't have anything here. We only have this. Okay, so R equivalent is equal to Rn. And you will realize that this Rn, or the Norton resistance, is same with the steps we have in R Thevenin, right? So R equivalent is basically equal to these two. Okay, so how to find Norton current? So you have this Norton current in parallel with Norton resistance, and same steps. You need first to remove any load if you have at terminals A and B here, and then make sure this is an open circuit. Okay, second, if you look at the circuit here, and in order for you to find this R Norton, what should you do? What if I connect this to a short path like this? What do you think the current will take? Is it going to be at IA here, IA path here, or IB path here? Which one? Certainly it will take the IA path here. Why? Because any elements in parallel with a shorted path like this, the current will bypass this R Norton. So basically this IA is equal to I short circuit, which is also equal to I Norton. So what should you do? You need to shorted the A and B terminals in order for you to find the IN. So the current direction will follow the this current IA. Okay, so this is how you have for your path or your steps for to find IN. Okay, let's see, we have this example and I change this question. This is basically the same question as your previous Thevenin equivalent, and you have two things. First is that you need to find R Norton. This is the same step as you did in Thevenin equivalent, so I will not really discuss on this. You need to replace the voltage source here with a short path, and then this R equivalent is equal to R Norton, and this basically equal to, oh, before that we can solve on the most left side here, this side first, and then they are in parallel, and then plus with 5k, they are in series. Then you will get this answer, and this basically equal to R Thevenin. In order to find the Norton current, you should use the circuit. Don't turn off the 50 volt independent source. At terminals A and B here, you need to short circuit this path, and the current of this short circuit path equal to the Norton current. Okay, then how to calculate this? Yes, you can do the source transformation. 50 divided by 2 kilo, you get 25 milliampere, and this is in parallel with 2k. Don't forget that 2k resistor, and you have this 220 kilo ohms, and the rest is same like this. Okay, and this 2k with 20 kilo, you can do the parallel rules, and what you will get is 1.8 1.818 kilo ohms. Okay, and then you can do the current divider. In order to find the Norton current, you need the source 25 milli and the opposite resistor kilo divided by 1.1k plus this 5 kilo here, and then equal to 6.666 milliampere. Okay, so this is a Norton current. Okay, just now we have the I Norton, which is equal to 6.666 milliampere, and R Norton is equal to 6.818 kilo ohms. If we use the Thevenin or Ohm's law, we will have I Norton into R Norton, which is equal to 6.666 milli into 6.818 kilo here, and this is basically equal to 45.45 volt, which is same as what we had in the previous video, right? So you can actually verify your answer using Ohm's law. Okay, and if you revisit your source transformation, this is like you source transform this. You transform the voltage source in series with resistor into what? Into a current source in parallel with a resistor, or vice versa. Okay. In this second video, this is revisit of our previous example. So in order to find I Norton, because we already discussed on the R Norton, so you need to remove the load. Whatever load you have here, you need to remove it. So what left is basically an open circuit like this. And then the next steps is you want to find I Norton, right? So what should you do? You need to connect the terminals A and B with a short circuit like this, and then you have I Norton here. So your approach is you can apply any methods you learn from chapter 1 up until chapter 4, this chapter. And then yeah, if you want to use source transformation also can. When you do the source transformation, this current source you can add, then you will get this. Yeah, you can continue your calculation and further source transform this part. 6 into 4 you get 24, and this one I change it to voltage source because you're going to transform this part, and this is 6. Since 6 with 6 they are in series, you can add, then this one will become 12. Okay, and then you can do the source transformation again. Have 12 here, and then 4 with a current source here, and the current source value is 2. 24 divided by 12, and then these 12 and 4 they are in parallel. You can combine using parallel rules. You get 3 here. Okay, so what is IN? IN is basically you need the source, and then 3 into 3 plus, since there are a shorted path like this, then it should be a true wire is equal to 0. Okay, R equal to 0. Then you do the math, you get 2 ampere. What about the R Norton? Yes, you need to turn off the independent sources, just like the Thevenin part. This is open circuit for 2 amps current source. Then you need to have, this is 4, this is A and B. No need to shorted this path. You need to find R equivalent. R equivalent is equal to R Norton, which is also equal to R Thevenin, right? So 6 and 6 are in series, you can plus, and then parallel with 4, and you will get 3 ohms. And from previous calculation, we get this result. Okay, so what is V Thevenin? You can calculate this to verify your answer. 3 into 2, because IN into RN, so you will get 6 volt, which is equal to what you already calculated in your previous method, Thevenin equivalent. So this verify that your Norton current and our Norton resistance both are correct. Okay, with that, I think that's all for this Norton and Thevenin equivalent or theorem chapter 4. We will continue next in maximum power transfer, inshallah. Thank you. Assalamualaikum.